Bum, bum. 11:01 it is. All right. I gave you some information on the upcoming test. There are going to be 10 questions on it, and with each question, I have like a pick from column A or pick from column B. You can do one of two problems. All right, so you can select which one you want to do, and if you end up doing both of them correctly, then you'll get some bonus points on top of just your regular points. All right. The questions are pretty well spread out between all of the sections that are going to be covered. And also remind you then that homework number 6 and the take-home quiz are due. Those are going to be really good practice. And in addition, that practice set, the solution is good to look over, and the solutions to the practice set are posted on Blackboard. And then, of course, there's the facts and formulas to know for the test, so be sure that you have a mastery of the items that are listed on that sheet. Okay. All right. Otherwise, I'm not going to take any more time discussing the test because we've got to cover a new section here today. If you do have any concerns, you can talk to me after class or email me. But I think it's good that you've got a choice for each particular question, whether you want to do one or the other. Okay. All right. So today we're skipping a few sections here, and we're on chapter 11. And this whole chapter 11 talks about sequences and series and representing functions in terms of infinite series. And I think it'll be, at least I hope it will be, a welcome change of pace from, say, the last unit, where we were just integrating and integrating and integrating, and so maybe this is something new, and it'll be welcome. At least I hope so. I do want to get covered then, hopefully, section 11.1 then today, and this section is called sequences, and this will lead us into the next section, which we'll look at on Friday, called series. Okay, so a sequence basically is just a list of numbers written in a definite order. Okay, so we have things like A1, of course that isn't a number, I understand, but A2, A3, A4, etc. And this is going to be the first term, that's the name we use for this. This is the second term, etc. So for every positive number, for every positive whole number, we have a corresponding number called A sub n. So let me write this down. For every positive whole number, we'll call it n. There's a corresponding number, A sub n. Okay. So let's just look at some examples of this rather than be so abstract about it. Examples, we can have A sub n equaling this expression right here, n over n plus 1. All right. So basically, A sub 1 means we're going to plug in 1 for the n. So it's going to be 1 over 1 plus 1. So A sub 1 is 1/2. A sub 2, we're going to plug in the 2. So we have 2 over 2 plus 1. and it's equal to 2/3, etc. All right. So now, this is one way that you can write or indicate a series. Another way that you can indicate a series is by using a bracket and putting the expression inside the brackets like that. That's the second way you could do this. And there's also a third way, which is very similar. Again, you use brackets, but then to the right of the bracket, you put in like the limit for the n number. Here, n is starting at the number 1, and it goes all the way up to infinity. Okay, there are an infinite number of terms in these sequences. Infinite number of terms. Okay. They can actually be thought of as a function that goes from the whole numbers to a number. So, can be thought of as a function whose domain is just the positive whole numbers. I.e., you can look at this a sub n as some function f applied to an integer n. All right, so we only apply these to integers and we get our numbers. Another example of a sequence would be something like a sub n equals the square root of n minus 3. Now, with this particular one, n is going to have to, our whole number n is going to have to start at the number 3 because otherwise we'll have a negative value under the square root. So this is for n bigger than or equal to 3. The point is this, they don't always have to start at the number 1, okay? They don't always have to start at that number n, that letter n equaling 1. Of course, another way I could write this series is, again, is put brackets and put the square root of n minus 3 in there. Or I could also write it with, again, brackets, square root of n minus 3, and then I could put my limits here. Here my n is starting at 3, so instead of n equal 1, I put n equal 3, and then up above I have n equal infinity. Okay. Let me show another example here. We're going to go through several things here. A sub n equaling 1 over n. That's another example. Or I could write it as 1 over n, or bracket 1 over n, n equal 1 at the bottom, n equal infinity at the top. And so with this one, a sub 1 is 1 over 1, which equals 1. A sub 2 is 1 over 2. A sub 3 is 1 over 3, etc. Okay, just plugging in whatever n value, integer value we have. Notice here that these numbers, the value of these terms keeps getting smaller and smaller. So I just want to point that out. The terms get closer and closer to 0 for that particular sequence. So it's just really a bunch of numbers all arranged 1, 2, 3 with subscripts 1, 2, 3, and etc. There are some sequences, though, that I can't really define so easily like I have right here. So let me put it this way. Some sequences don't have what's called a simple defining function. So here's one example. Let's say we have a sequence that starts at 1, and then our second number, a sub 2, is 0. and then the next one is 1, and now we have 0, we have 2 zeros following that. So this is a 1, a 2, a 3, a 4, a 5. Then we have another 1 again, and now it's followed by 3 zeros. Then we have a 1, and then it's followed by 4 zeros, etc., like that. So there's no way that I can write a nice little function to indicate this pattern of numbers. So that's one situation. We can also have a sequence that's defined what we call recursively. We can have a sequence that is defined quote-unquote recursively. So let me give you the most famous example of a recursively defined sequence. It starts at 1, and then the next number is 1, and then the next number is the sum of the previous two numbers. 1 and 1 is 2. My next number here is going to be the sum of the previous two numbers, so 1 plus 2 is 3. My next number is going to be the sum of 2 and 3, 5. My next number is going to be the sum of 5 and 3, 8, 13. What would be my next number here? 21, etc. There's a name for this kind of sequence. Anybody know the name? Fibonacci sequence? Yep. Very good, Roland. Fibonacci sequence. It's actually, if you Google it, you'll find it's found a lot in nature. Don't ask me right now. I just was going to put that out as an FYI. I didn't prep that, but it's actually in the patterns of things that you see. You'll see this kind of increase in numbers. So I'm sorry. If I was even going to say that, I should have then backed it up by looking at it. Somehow I'm wanting to think of like a flower petals. I'm not sure why I'm thinking that. So maybe you can prepare that for Friday. It's defined recursively, which means that any part of this is defined as the sum of the previous two. So it's actually A1 is, the first term is 1, the second term is 1, but then after that, say A sub n, it's the sum of the previous two terms. So it's equal to A sub n minus 1, which is the previous term, plus A sub n minus 2, which is the term before that. And that's why it is considered recursive in nature. Okay. All right. Now, let's talk about a limit here. This is an important concept here with sequences. So let me put a star here, meaning it's an important thing. A sequence, and we usually are going to put like this bracket, A sub n, inside the bracket, has a limit. We'll call the limit capital L if the terms of the sequence, that's the individual members, if the terms A sub n get as close as we want to some finite number L as the ends, as the subscripts get bigger and bigger. As the subscripts n get larger and larger. Okay. So the numbers get closer and closer to one finite number. And let's write this a little bit more, shall we say, mathematically here. This is what we do. For one, if it has a limit, a finite limit, we say that the sequence converges. Okay. So if it has a finite limit, it converges, and we write it a little bit more mathematically like this. We write LIM, and then below it, n arrow infinity, as n approaches infinity, and then we put whatever our sequence is, I'll just put a sub n, and then we put equals L, whatever that finite number is. Okay. Now, one of the sequences that we looked at earlier, a sub n equaling 1 over n, we saw that it got closer and closer to 0. So therefore, this sequence has a limit. So therefore, the LIM as n approaches infinity, and then we could write here, usually you'll put it in brackets, just write in the sequence like that, 1 over n, and so its limit is 0 then, as the n's get bigger and bigger. Okay. Obviously, it converges. Okay. So let's look at another kind of sequence that goes to 0. You may or may not recall that in Calc 1, it was shown that the limit as x approaches infinity of 1 over x to the r power is equal to 0 if r is any number bigger than 0. Okay. All right. So therefore, we can use this fact, because say we have, say it's 1 over x squared, say that is our function. As x gets bigger and bigger, the number below is going to get real big and bigger because it's squaring it. And so with a real big number in the denominator, you're going to have it go to 0 as its limit. So now what if x were negative 2, so it has to be a positive number. If it's 1 over x to the minus 2 power, how can I rewrite that? Yeah, it's x squared. I can bring it out of the denominator and write it as x squared. Now, as x gets bigger and bigger and bigger, x squared is going to get real big too, and that's actually going to go to infinity, not 0. Okay, so it has to be a positive number. All right, so we can use this fact. Whoops, how about putting u's in here? We can use this fact to say that for a sub n equaling 1 over n to the r power, where r is any number bigger than 0, so that's our sequence term, how it's defined, then the limit, LIM, as n goes to infinity, of 1 over n to the r power is going to be equal to the 0. And again, that's if r, the exponent, is bigger than 0. Okay. So this is something, let me put some stars by that. That's a fact that we want to keep in mind. All right. Okay, so we're talking about looking at limit values. We can actually use kind of basic arithmetic to find limit values. Let me put this statement down. We can use some basic arithmetic to find limit values. All right. So let's show you what I mean by that. Examples. Let's have a sequence defined like this. So we have a sub n equals the number 4 plus 1/2 raised to the n power. So this is how we're defining each term of our sequence. And we want to find the limit of a sub n as n goes to infinity. Okay. This can be broken up like this, as the limit of the number 4 as n goes to infinity plus the limit as n goes to infinity of the second term, 1/2 to the n power. Now that first one, the limit of 4 as n goes to infinity, well, it doesn't even have an n in it. So that's not even going to change value at all. As n gets bigger, it's still going to be the number 4. So this is the number 4 right there for that first limit. All I'm doing is breaking it apart. Now my second limit, 1/2 raised to the n power, let's see, what's that going to be? We're going to have 1/2, 1/4, 1/8, 1/16, etc. What's the limit of that going to be? 0. They're all getting smaller and smaller and smaller. So the limit of the second one is 0. Sometimes it can be very helpful just to write out a few of the terms. And so 4 plus 0 is 4. So that's the limit of my original sequence, just by breaking it apart. Now, continuing with this, let's define another sequence. Let's now call it b sub n. And let's define it as the square root of what I had previously written, 4 plus 1/2 to the n power. And we want to find the limit as n goes to infinity of bn. All right. Well, we found that what's under the radical approaches the number 4. We just did that in the previous problem. So the limit here is that it's taking the square root of that limit that we just found that's under the radical. And so the square root of 4 is 2, and that's our answer. So this is kind of like we can do kind of arithmetic stuff on these limits to find a new limit for a new expression, all right? Here all we're doing now is doing the square root. Does that make sense? Jenna, does that make sense? All right, okay, all right. Okay. Again, we're focusing on limits. That's really the big thing in this section. Let me put this back down here and give a couple of examples here of this. If a sequence equals the values of a function or the value of a function at the positive integers and if the function has a limit capital L as x goes to infinity, then we can conclude that the sequence has a limit capital L as n, or numbers, go up and up to infinity. So I think the best way to kind of illustrate this is with an example here. Let's look at this. Look at a sub n defined as follows: the natural log of n, where n is equal to 1, 2, 3, etc. Okay. And we're asked to find the limit as n approaches infinity of a sub n. All right. So notice, every term of this sequence is basically a natural log value, except it's at an integer. So the corresponding function is the natural log of x. All right? It just takes on the values of the integer. Now, we know, or we should know, that the limit as x goes to infinity of the natural log of x is equal to infinity. The natural log keeps getting bigger and bigger, so this equals to infinity. So since that underlying function limit is infinity as x gets bigger and bigger and bigger, then my sequence values are going to also approach infinity. Thus, the limit as n approaches infinity of a sub n, our sequence, is also equal to infinity. Now, when the limit is equal to infinity, infinity is not a finite number, so it diverges. We say it diverges to infinity. It does not converge because it's not a finite number. So it diverges to infinity. I want to do two more examples of this kind of thing. Let's do another example. Here we have our sequence a sub n is defined as the sign applied to n times pi all divided by 2, like this, where n equals 1, 2, 3, etc. All right. So let's look at this. What is a sub 1 equal to? A sub 1 is equal to the sign, n is 1, 1 times pi over 2. So the sine of pi over 2 is 1, right? Sine of 90 degrees. What's a sub 2? A sub 2 is the sine of, now n is equal to 2, 2 times pi over 2, which, when I simplify, is equal to the sine of pi, and that's equal to 0. A sub 3, when we plug in 3 for n, is going to be the sine of 3 pi over 2. And what's the sine of 3 halves pi? Negative 1. And then I'll just do this last one. A sub 4 then is when n is equal to 4, so that's going to end up being 4 pi over 2, which is the sine of 2 pi, and that's equal to 0. And then it's going to keep repeating all the way around. So we have 1, 0, minus 1, and it just keeps circulating around. So would something like this converge to a finite number if it just keeps cycling amongst different numbers? No. So it therefore does not converge. We can then say it diverges. All right. Okay. Another one involving a trig function is something like this. Let a sub n equal the tan inverse of the number n. All right. And we want to find the limit as n goes to infinity of a sub n. Okay. So in this case, our underlying function is tan inverse of x. Underlying function is tan inverse of x. Now, so we look at what happens when x goes to infinity. What is the limit as x goes to infinity of the tan inverse of x? We've discussed this in class before. It's pi over something. Not pi over 4, it's pi over 2. Yeah. Because as we get up to pi over 2, remember the tangent is the sine over the cosine, and cosine gets smaller and smaller as we get to pi over 2. So therefore it gets larger and larger, it goes to infinity. So the limit of the tan inverse of x is pi over 2. In fact, I think that's also one of the formulas little things I have on that facts and formula sheet. So therefore, because we know that that limit is pi over 2, thus the limit as n goes to infinity of a sub n is also equal to pi over 2, because of the underlying function. All right. Okay. How about looking at find the limit as n approaches infinity of n divided by n plus 1. And let's also put another one down here. Let's also find the limit as n approaches infinity of n squared over n plus 1. Now, how do we approach these? Because the top is going to go to infinity, and the bottom's also going to go to infinity. Well, I knew somebody was going to say that, and I'm glad you did. But there's an easier way. We could do that. But there's actually, for this case, there's an easier way to do this. For these kinds of things where we just have these little polynomials divided by a polynomial, the trick is divide each term by the highest exponent of n. So this is the trick. Divide each term by the largest exponent of n. By the largest exponent of n. So, in the first one, the biggest exponent of n is n to the first power. So I'm going to divide n by n to the first. I'm going to do that. That's my top term. Now I have two terms in the bottom. I divide the n by an n, and then I have a plus, and then I divide the 1 by an n. Now we get something that is equivalent, but looks a lot different. So now we're looking at the limit as n approaches infinity of this. On the top, n over n is equal to 1. Down here at the bottom, n over n is equal to 1. Plus, and now we have 1 over n. Now look at what do we think the limit of this might be as that number n keeps getting bigger and bigger? No, 1. It's going to equal 1. this is going to equal 0. 1 over n, as n gets bigger and bigger and bigger, this is going to go to 0. But that's not the only thing we have in our expression. The top is strictly the number 1. On the bottom, we have the number 1 plus this expression that goes to 0. So basically, this limit is going to be 1 over 1 plus 0, which is equal to 1. That's going to be our limit. All right, part of it goes to 0, but not the whole thing. Now let's contrast it with this one, the second one. What's the biggest power of n that I have in my expression? The squared, 2. So I'm going to divide each term, so this equals the limit as n approaches infinity. And I'm going to divide each term by n squared. So on the top, I have n squared, and I'm going to divide that by n squared. On the bottom, I have n, and I'm going to divide that by n squared, plus, and I have a 1, and I'm going to divide that by n squared, all the individual terms. Now let's rewrite this and see what we come up with. So this is the limit as n goes to infinity of what? Well, first of all, n squared over n squared, in the numerator, I'm going to have the number 1. Now, in the denominator, n over n squared, I cancel out an n, and that gives me 1 over n. Plus, and then the second term is 1 over n squared. All right, now let's see what this gives us. As n gets bigger, what does this one term go to? It goes to 0. And what about this other term in the denominator as n gets bigger? 1 over n squared. It also goes to 0. But that denominator, n squared, is going to get larger and larger. So look what happens here. Both of the terms in the denominator are getting smaller and smaller and smaller. They're going to 0, right? So if all the denominator is going to a 0, what's my entire expression going to? If it keeps dividing by smaller and smaller numbers. No, it's going to go to infinity. Because as we divide by smaller and smaller numbers, we get bigger and bigger numbers. So this limit here is infinity. All right, which means it diverges to infinity. Okay. So remember, let me put an asterisk here. Remember this little trick here, because you're going to see it in your homework at a couple of problems, of dividing all the terms by that biggest power of n. All right. Now, let's look at a sub n equaling this, minus 1 raised to the n power divided by, let's say 5 to the n power. Okay, so this is how our sequence is defined. So therefore, let's look at a sub 1. We replace n by 1. We're going to get minus 1 up above and 5 down below. So it's negative 1/5. Let's look at what a sub 2 looks like. We plug in 2 for the n, so minus 1 squared is going to give me a positive 1. And down below, I'm going to have 5 squared, or 25. Let's just look at one more term here. A sub 3, I'm going to have minus 1 raised to the third power, so I'm going to go back to negative 1 in the numerator, and then 5 to the third power is 125. So just from these few terms here, what do we think the terms of this sequence converges to? Are they getting smaller? It's going to get closer to 0, right? We're getting smaller and smaller numbers. I mean, If it would have helped, I could have gone through another one. A to the fourth minus 1 to the fourth power is 1. 5 to the fourth power, I think, is 625. So you see that denominator keeps getting bigger and bigger and bigger. Yeah, Shannon?
Does it matter that some of them are negative and some are fractions?
Okay, that's actually the point that I'm coming across here with this. But thanks for noticing that. All right. This is the fact that we're leading up to here. If, and this, let me put an asterisk by this fact. If we do the absolute value of the sequence values, so if the limit of the absolute value of a sub n, as n goes to infinity, if that is equal to 0, then the sequence itself without the absolute value equals 0 also. All right. So that's exactly what we have up here. If we look at this above one up here, the absolute value of a sub n is the absolute value of minus 1 to the nth power over 5 to the nth power. Well, the top is it's always going to be positive. The top is always going to be a 1. And the bottom is going to be 5 to the nth power. It's always going to be a positive because it's an absolute value. And we know then that the limit of 1 over 5 to the n, this absolute value, as my exponent n there keeps getting bigger and bigger, that's going to equal 0. So since the limit of my absolute value is equal to 0, I can say thus then the limit of the original minus 1 to the n power over 5 to the n is equal to 0. Okay. And this is, if we look at a number line, this is really what we're talking about. Let's put 0 on the number line. So let's just look at a sequence. Say we have a sub 1 here on the positive side, and then we have a sub 2 here, and then a sub 3 is back over on the positive side, but it's a little bit less. A sub 4 is back on the negative side, but it's a little bit less. And then we have a sub 5, a sub 6. They keep getting, although they flip signs, they keep getting smaller and smaller and approach 0. So therefore, the limit of those sequences, of those terms, is equal to 0. Okay. All right. What we're going to look at next is we're going to see in the next section on Friday. So let's look at this. For what values of R is the sequence R raised to the n power convergent? So what we're doing here is every term has a new higher power of the exponent, okay? So in other words, we're talking about R to the first, R to the second, R to the third, R to the fourth, etc., like that. That's what our sequence looks like. Okay. Now, let's look at, first of all, suppose the absolute value of R is less than 1. That means that R is crammed or kind of squeezed between -1 and +1 if its absolute value is less than 1. Let's look at the limit of the absolute value of our AN and see what we get here. Okay, now we're looking at absolute value of our AN. So this is absolute value of the AN. And this is equivalent to the limit as n approaches infinity. I can put the absolute value down just around the r. So this is just something from algebra. The absolute value of r to the n power is equal to the absolute value of r taken to the n power. It's just an algebra thing. All right. Now, if r is less than 1, so the absolute value of r is less than 1, let's say it's 1/3, then our sequence is going to be, this is going to be 1/3 to the first power, 1/3 squared, which is 1/9, 1/3 cubed, which is 1/27, 1/3 to the fourth power, which is 1/81. So we see that if r is some fraction less than 1, if its absolute value is less than 1, this is going to go to smaller and smaller numbers, and the limit is 0. The limit of the terms goes to 0. And that's if the absolute value of r is less than 1. Does everybody see that? They just keep, as we multiply them by themselves, they just keep getting smaller and smaller. All right. So we can conclude, first of all, that if the absolute value of r is less than 1, then r to the n converges, and it converges to 0. All right. Now, what about if r is equal to 1? Well, then our sequence is then going to be 1 to the first power, 1 to the second power, 1 to the third power, 1 to the fourth power. Every value is equal to 1. Then, if r is equal to 1, then then the limit as n approaches infinity of r to the n is equal to 1. And finally, if our absolute value of r is bigger than 1, these numbers are going to keep getting bigger and bigger and bigger, and so the limit of r to the n as n goes to infinity is equal to infinity. All right. Actually, well, let me just say this. It diverges. I should say that. Let me just write this whole page in one little thing here, because we're going to use this in the next section. The limit as n goes to infinity, and then I guess we're just about ready to stop. The limit as n goes to infinity of r to the n power is equal to the following. It's equal to 0 if the absolute value of r is less than 1. It's equal to 1 if r is equal to 1. And otherwise, it diverges. What happens if r were equal to -1? I really didn't specifically mention that. So this is our sequence. It's r to the n power, but our r is a -1. So here we have -1 to the first power. That's our first term. -1 to the second power. -1 to the third power. -1 to the fourth power, etc. Well, what do we get then with this thing? They just go back and forth, because when we have an odd power, it's -1. When we have an even power, it's 1. So it just flips back and forth. It doesn't converge to a single number. So therefore, it diverges for that. So this fact here, when the absolute value is less than 1, r to the n goes to 0. That's something that we're going to see in the next section. Let's see where we are here. Okay. We're out of time here. There's just a little bit more in this section that we'll start with on Friday and go on from there. Anyway, I hope that once the black cloud of the test is over with, you can start to enjoy something different here with this section. Thanks. Oh, but I didn't have done it Friday. Okay, I'll look at it also. All right.
By the way, you were right with the flowers. Only found different flavors. And you can do flowers.
Did you look?
Yeah.
You only found in picture.
Flowers.
They only found flowers.
You will never find them except for 4 leaf clovers if you consider them flowers. That's why it's not just because it's a rare thing. It's actually the only one I've been told.
Okay. So I knew it had something to do with patterns and flowers or something, but beyond that.
Yeah. Oh my God. 4 leaf clovers.
Oh, I got to get moving. But we got.
I ask you to help me with something.
You weren't going to put me to work.
I can't use these things. I don't know how they.
All right.
Sometimes they function like they're supposed to.
All right.
The reason I know it's not always me is because I've had somebody come in and he's like, "This is not supposed to work like this."
Let me stop my recording here, and then let me.
I'm a little confused.